Okay, so this is a warm-up to section 13B, which is going to cover scalar line integrals. So I want you to find the length of this curve described here. This is a flashback to chapter 10. Go ahead and put this on pause and see if you can remember. Okay, let's go ahead first and visualize this. I'm just going to do a little animation. This is part of a helix. That blue vector is the vector r of t that's tracing out the curve. And some of you may have said, wait, this looks familiar. And if you notice, this was exactly the curve that you had in problem 2 from exam 1. And in fact, you had to find this exact thing in that problem because this problem said how much further does the particle travel along this curve than if it went directly. So the first thing you needed to find for this problem, 2a, was actually the length of the curve the particle travels along this helix. So let's go back and remind ourselves how we do this. This is a screenshot from my notes from that section back in chapter 10. And basically, I just wanted to recap for you how we find arc length of a curve. And the idea is we're chopping it up into little segments and then estimating the length of the segments using lines. And then we're taking the limit as those segments get smaller and smaller. In this case, that's going to lead us to, we're integrating the speed times the time, r prime of t, or your velocity, dt. So let's go do this for this problem. And then I want us to extend that, or think of how we could extend that idea in the case that we wanted to find something more about this curve, like maybe the mass given the density, or the average temperature along the curve given some temperature at each point, etc. Okay, so recall from the exam, you can find this arc length by integrating the speed, dt, and that's going to end up just being the integral of 3, because in this case, this parameterization had a constant speed. 3 dt from 0 to pi will just be 3 pi. But I want us to notice that another way we could think about this, and I'm just going to resketch part of the, so just suppose this is part of the helix. I know it didn't do as many loops. Maybe we stopped right around there or something. But what we've really done when we chopped it up and approximated the distance along each piece was we're integrating along this curve. But what we're actually adding up everywhere is a tiny little distance. And remember, we had a way from chapter 10 to describe how far we'd gone along a curve. We used the arc length parameter, s. And so really, I could think of this as adding up a bunch of tiny little delta s's, taking the limit as I chop it up into more and more, and that'll give me the overall total length of the curve. In this case, I can write that as this integral over the curve ds. And so this is an example of what we call a scalar line integral, because we're adding up over a curve. In this case, I'm just adding up an integral of ds, which gives me physically the arc length. But I want you to notice how you actually calculate it, which you learned in chapter 10, is to change variables. And when you change variables, you see that ds is replaced with your speed dt. So really what we were doing back in chapter 10 without even realizing it is we were using a transformation from an integral in terms of s, rewriting it to be an integral in terms of t, where this speed is actually the equivalent of the Jacobian of the transformation. And so we're going to extend this now and say, what if I wanted to find a line integral of something that had more than just ds in the integrand? What if I have some function here in the integrand? Oh, let's put a different color. And maybe this function represents the density along that helix at any point. Maybe it represents temperature. And I could integrate this function here over the curve. And we're going to see that the method will be very similar. I'm going to need to change variables, just like I did up here. I will need to replace my ds with the Jacobian, which is the speed, dt. And then I will need to also rewrite my integrand now to be all in terms of t. So let's talk about this in more detail, and we'll write it out in the handout for this section.